In this video, I want to take a look at how we solve second-order homogeneous equations when there's constant coefficients. So we got something that looks like this. AY double prime plus BY prime plus CY equals 0. Now, we don't have any method yet, so at this point it's just a matter of, is there functions that we think might work, and then maybe we can work with that. So I'm looking at this thinking, I need a function y whose derivative and second derivative look enough like the original function that I can combine them by just multiplying by constants and adding. And I'm just taking a linear combination of y prime, and y double prime. So you got any functions that look like their derivative and their second derivative? Things that come to mind for me are polynomials, because the derivative of a polynomial is a polynomial. Certainly exponential functions. You take the derivative of any exponential, you get that same exponential back. Maybe times a constant, depending on what's in the exponent. But sines and cosines also. Take the derivative of a sine, you get a cosine. Take the derivative of the cosine, you get a sine. That might be a problem, though, with the y prime in here. Because if y is a sine, then the derivative is cosine and the second derivative is negative sine. So these two might combine, but not that one. Likewise with cosine. But actually, if you add sine and cosine together, then the derivative would be a sum or a difference of sines and cosines. And so definitely sines and cosines are going to be a possibility here. Polynomials, it turns out, aren't. Because, I mean, think about it. If y is a cubic polynomial, then the derivative would be second degree, and the second derivative would be first degree. But there's no way this is going to add up to 0 because that cubic polynomial has a cubic term. But the derivative and the second derivative don't have cubic terms to cancel out the cubic term. So the crossed out polynomials here definitely not going to do that. But exponentials, sines and cosines, yeah, we're going to see those come up. But let's start with just an exponential. Let's say, suppose we think this looks like y equals e to the rt for some r, that an exponential function might work in here. Let's plug it in and see if we can find a value of r to make it work. And so if y is e to the rt, then the derivative is r e to the rt, and the second derivative would be r squared e to the rt, and plug these in. The r squared e to the rt goes for the second derivative, r e to the rt there, and e to the rt for y, and we get this. I notice that there's an e to the rt in each one of those terms, and so I can factor it out, leaving just this. But now I've got a product of two things equaling 0, and hey, I know how to handle products equaling 0 because there's only one way to do it. If you've got two numbers that multiply to be 0, one or the other, or both, have to be 0. So either this thing in parentheses is 0, or that exponential is equal to 0. But the exponential is never equal to 0, because e to a power is going to be a positive number, not 0. So that leaves us with the equation ar squared plus br plus c equals 0. This is a quadratic equation. Notice that the coefficients a, b, and c are the same as the coefficients that we had here, a, b, and c. And that's going to be the case every time. This is what's called the characteristic equation for this differential equation. And if I can solve this for r, I can find solutions. And it's a quadratic equation. I know from my algebra days that there's two solutions, right? The quadratic equations have as many as two solutions. And so let's just call them R1 and R2. How would you find it? Well, if you could factor, of course you'd factor, or you could use a quadratic formula or whatever. There's several ways to solve it. But I just wanted, for this discussion, to say I know that there's two solutions. I'm going to call them R1 and R2. And so, remember, r was used to be e to the rt, and I was looking for values of r that would make e to the rt a solution to this differential equation. And so I've got two solutions, e to the r1t and e to the r2t. Okay. Now, I want to slide up here. I see that, actually I'm going to move my face so that I'm out of the way. There we go. In second order homogeneous equations here, if I've got one solution, it turns out I have infinitely many solutions because I can just multiply by a constant, right? If y is a solution, then I claim that ky is also the solution. And here's how I would prove that. I'm just going to take ky and plug it into the left-hand side of this differential equation. Where was it? I'm plugging the left-hand side of this, ky, I'm plugging in for y, and see if I get 0. See if it works, right? So here we go. Ky is plugged in for y each time. This one I'm just multiplying by c. This one I'm taking the derivative and then multiplying by b. And this one I'm taking the second derivative and multiplying by a. But the derivative of a constant times the function is just the constant times the derivative. And likewise, the second derivative of a constant times the function is just the constant times the second derivative. That constant just comes along for the ride when it's being multiplied. But now I've got this thing with a k in each term, and I can factor the k out, leaving just this on the inside. Well, that stuff on the inside of the parentheses is what you would get if you plugged y into the left-hand side of that equation. And we know that y is a solution to that differential equation, right? If we have y as a solution, then so is this. So we're assuming y is a solution, which means that the stuff inside parentheses there is equal to 0. And what I have is k times 0, which is also 0, which tells me that ky is a solution to that differential equation. Okay. Furthermore, if I've got two solutions, it turns out I can add them together to get a third solution. So, for instance, if y1 and y2 are both solutions, let's check, is y1 plus y2 a solution? And it is. So here's how we know that. So I'm plugging y1 plus y2 into the place where y is on the left-hand side of the differential equation. So I've got y1 plus y2 second derivative times a, y1 plus y2 first derivative times b, plus c times y2, and I'm going to see if I can show that that's equal to 0 so that it is indeed a solution. But how do you take the derivative of a sum? Well, you take the sum of the derivatives. How do you take the second derivative of a sum? Well, you take the first derivative and then you take the second derivative, but you still end up with the sum of the second derivatives. Now, there's a distributive property that allows me to multiply the a and the b and the c in here, giving this. And then I'm recollecting things together. Everything that's got a y1 in it, I'm putting first. And everyone that's got a y2 in it, I'm putting second. And I seem to have managed to make this long enough that... So, yeah, this is too long to see on the screen. And so let's put it down here. What we have in the first parentheses is equal to 0 because y1, we said, is a solution to the differential equation. And the second one is also a 0 because y2 is a solution to the differential equation. And when you plug y2 into that left-hand side, you should get something that's equal to the right-hand side. So we've got 0 plus 0, which is equal to 0, which tells me that y1 plus y2 is also a solution. So if I have two solutions, then I can write down this, constant 1 times the first one plus a constant 2 times the second one. And that sum will be, that linear combination of y1 and y2 will also be a solution. Okay. And it turns out that if y1 and y2 are independent of each other, whatever that means, we'll talk about that in the next section, then I have a general solution. That is, all the solutions look like c1 e to the r1t plus c2 e to the r2t. Okay. Now, there's some things that could go wrong here, right? I was assuming that these were exponential functions as a solution. And it turns out that if indeed you do get two solutions, r1 and r2, that are real numbers, then this is precisely right. Now, if you get that quadratic equation with only one solution, or maybe no real solutions, then, well, if you get just one solution, then certainly you have a solution. The question is, what's the other one? There's got to be another. It turns out that you'll always need two independent solutions here. And if you get complex roots, what do you do? If r1 and r2 are, complex numbers, what do you do? Well, we will look at those things in later sections. What do you do in each of those cases when you only have one real solution to that quadratic equation, or if you have two complex solutions, what happens? It's all very predictable and leads to some interesting algebra about complex numbers, so we will look into that in the future. In the meantime, we probably need to do an example, but I'm going to save that for the next video.